लाइट लाइट ऑन है इधर कर देते All right, good morning, everyone. I hope you're able to hear me properly. Let's start with the quiz. Now, the quiz was that you were supposed to write a deep neural network, and we are supposed to import date from date time and then date time dot now, so we can actually figure out you've done it on time or not. You're also supposed to your own module. Now, it calls a particular DNN from a quiz DNN.py file, and this was the DNN which you were supposed to write. It uses ReLU and batch nomination wherever applicable. You use the FAR10 as dataset, target is 75% less than 40 box. Once done, paste the code in the quiz DNN PY, paste the code of your collab notebook, paste the complete training log, paste the link to your Google Colab. Now, because we don't have answers to discuss, there's not much we are going to spend on the quiz. I hope you have spent enough effort on the quiz, and I'll be reviewing this quiz in like a couple of days. There's nothing on the quiz as of now. You have any question, you can just post on the side chat window. I'll take it from there. Okay, let's start into this session. Now, today's session is on advanced concepts, and this is on training and learning rates. Let's still wait for a few minutes in case you have any question. Okay, irrespective, let's go GradCam again. This is just in case you were not able to understand this in the last session. Then we'll start the main today's session. So the process was that we take an image, and this image is made to go through a particular DNN. Then we wait for L minus 1 layer. This layer is supposed to have at least 7 cross 7 as the resolution, and 5 cross 5 will also work, but your gradients are not going to look very good. So we need to be at a channel where the size is 7 cross 7. Now, after this, you may not have a fully connected layer, but the idea is that whatever outputs are going to softmax layer, we are going to be focusing on that. Now, this is softmax output, and right now we are working on Tiger Cat. And I'm saying we are working on Tiger Cat because if you see the image, we have a dog and we have Tiger Cat both. But we are working on Tiger Cat, which means if we had dog and we repeat the same experiment for a dog, we are still going to get the heat map, but this time for a dog. But we are not doing that. We are working with Tiger Cat. Okay. So let's say we work for Tiger Cat. What we do is we take this particular channel, and let's say this channel is 7 cross 7. We take a particular pixel. We calculate the gradient change of cat with respect to this particular pixel. This is this pixel. Let's say we call this px1. So this is px1. and we do this for every single pixel. So we do it for this one and 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 this one. So we're going to do it 49 times for each channel because we have 49 pixels, and that gives us these channels, right? Now the idea here is that if we reduce pixel px1 and the class probability or the softness value also reduces, that means that these two are positively correlated, which means if I increase this will also increase. So just calculating derivative helps us understand whether the channel itself is positively correlated or not, because if all the pixels are positively correlated, then the channel is also positively correlated. So that's the idea. And then we do a gap of these channels, and after doing the gap, if all the pixels of a particular channel were positively correlated, the whole channel will be positively correlated, which means we'll have positive values for the channel where they are supposed to be helping prediction of cat, and we'll have negative numbers. I'm writing just one just for as a hint here, but the sign is what is important, because number is not going to be 1, because we're taking a mean of all these channels. Now, after doing this particular step, after taking the gap of these channels, we multiply the original channels. Now, the channels which are related for the cat, now they're going to get higher amplitude. They're going to be positive also, and they're going to be multiplied with a big number. But if they're negatively correlated, they're going to be suppressed. They're going to be multiplied with negative number, and then we take a gap. Then we take then we do an addition, which means we convert 7 cross 7 cross 5 and 12 into 7 cross 7 cross 1, right? And after that we do ReLU, and once we perform ReLU, we get only the positive pixels which are linked for our prediction for tiger cat, and that is what we call a heat map, and that is what we overlay on top of our image. So that was the overall algorithm which we looked at in the last session. Okay, now let's start with today's session. Okay, still a few people. Okay, so advanced concepts. Today we're going to cover training and learning rates. Now, what is a learning rate? Learning rate is a hyperparameter that controls how much we are adjusting the weights of our network and with respect to the loss gradient. Okay, we're going to look deeper in this, so don't worry. The lower the value, the slower we travel along the downward slope. If we move slow, there's a good chance we are going to reach our minimum, but it's going to take a long time to converge. If we move fast, we're going to reduce the loss faster, but the minimum will also elude us. This is how we calculate loss, right? Now, this is an important equation, so let's important graph, so let's look at that. All right. So this is our input, and let us say our input is an image. So we have an image which is coming in. These are the kernel weights which we are using for performing convolution. Data transformation means whenever we convolve and whenever we change our data from one specific channel to another channel, we call that data transformation. So we have our layer 1, and then we have a layer 2, and after that we do our prediction. So network architecture doesn't matter. Overall, we are trying to look at how the networks are structured with respect to the loss. Now, in the loss function, we have our predictions, and then we have our targets. We compare these two, and then we look at the loss score which we have. Now, we covered NNL, negative log likelihood, as a loss, but let's keep it simple and see. Let us say that we actually wanted our loss to be, let's say the prediction for a particular image to be 1001. Oh, sorry, 1000. So we have 1, 2, 3, 4, 5 classes, but our prediction was 0.6, 0.3, 0.1, 0.0, and 0.0, right? So we had this kind of prediction. So we wanted one hot vector as an output, but we are right now predicting a high value for this, but we have some other values also. So overall, our loss is going to be calculated like this. Let's say we are just looking at the L1 loss. It's also called Huber loss. So we have 0.6, and then 0.3, and then 0.1, and then 0 and 0. This is going to be compared with 0. Is going to be compared with 1, 0, 0, 0, and 0, and then we have negative in all of them. So we're going to compare 1 minus 0.6 whole square. Let's say, yeah, sorry, we are looking at L2 loss, plus 0 minus 0.3 whole square, plus 0 minus 0.1 whole square, plus 0 minus 0 whole square, plus 0 minus 0 whole square, right? So that is how we are going to write a loss. And whatever this sums up to, we could have used our NNL loss as well, but that's going to give us a particular score. right? So this is how the things are structured. Okay. Now this is how the gradients are related to a loss function. So let's look at this particular part. Okay. Now I want to just work on this particular line. The lower the value, the slower we travel along the downward slope. Now that will be clear from this particular image. So let me just copy that. Okay. Now if you see our first of all, there are many things which are hidden in this particular image. You see this is our weight, and our weight takes a bigger step, then a smaller step, then a smaller step, then a smaller step, then even a smaller step, and so on. This is how we want to travel across a loss curve. Now, this is very important to realize. First of all, this curve which you're seeing right now is a fixed curve at a particular instant. Your loss curve is going to change always. So let's understand this point. What exactly I'm trying to tell you. What I'm telling you is this curve which you are seeing, let's say we are able to draw a loss curve of our weight, right? So if changing the weight, how the loss changes, let's say we can draw that particular curve. This particular curve is a fixed curve for a particular time t. This curve is going to look like this only at this particular time, and after that it's going to change. Now why is that? Now our loss, if we saw the equation also, right? So our loss was equal to y, which is, let's say we are predicting, minus y targets, right? Let's say we keep it a very simple loss. Now if you see the loss which we are predicting, or the label which we are predicting, now that depends on every single x we have, which is the input, but it also depends on every single w we have, right? Our inputs may be fixed because in let's say one full epoch we are going to look at every single image, that's fine, but the weights are changing, right? Now when we have, let's say, 100 weights, we are looking at the current weights right now. So if I just write my loss, I can say my loss is sort of dependent on the weights I have. So if the weights change, the loss curve is also going to change. So the curve you're seeing right now is a fixed curve only for a particular instant. It's going to be looking very different next time you look at the next batch or even next epoch, right? So this is something you need to realize, that this is a constantly changing and constantly shifting curve. Now, difficult to let's say realize how this might have happened, but imagine that you have this particular curve, right? Imagine that this is the curve we have and this is where the variable is. Now, as the variable is coming down, because you want to hit the minimum, as the variable is coming down, the curve also shifts, right? And it's going to happen in a huge dimension. Right now you're seeing only two dimensions because we're only drawing the loss versus the w curve. So if we are able to see our curve in two dimension itself, again in that particular case our curve will be shifting depending on how other variables are behaving, right? So imagine that this is kept on Bangalore road, so it's going to go up and down, left and right, but our ball is still trying to reach at this particular point. So this is the first thing you need to realize, because I'm going to explain to you that how we actually want to look at the loss curves and try and link them to something we can follow. Second, you need to realize is that in this graph, it is shown that we are reducing the value of the steps we are taking when we are going towards our final minimum. Now, this is very important because this is also something you do when you are driving your cars or bikes. When you go to your house or when you approach your house, let's say you're starting from airport, you're in a hurry, so you're going to start very fast, and on the highway you're going to touch 100 kilometers an hour also. But the moment you are very close to your house, you're going to slow down, right? And you're going to slow down because you want to stop exactly at that particular point. Otherwise, you're going to shoot. That is precisely the idea here. Let us say that you have a car where you have a button. This is that button, and when you press this button you can move at the speed of light, right? So if you move at the speed of light when you're at airport, let's say we click and we have just unclicked, within that time you would have reached Chandigarh, and then you click it again because you've already overshot. When you click again, you might go to Mysore, right? When you click again, you might go to Sri Lanka now. So it depends on how fast you're moving. You will never be able to settle down exactly at the point you want. But just a fraction of nanosecond, in fraction of nanoseconds, you would have crossed thousands of kilometers. So we don't want that. We want a particular speed in which we want to travel to our house. Let's say that we travel very slow, and if we travel very slow, let's say we are sitting on a snail, it will be like 40 years before you are even able to reach Hebbal from the airport, right? So we need to be at a speed where it is suitable for us. What we're trying to say is that if our learning rate is very high, you might actually just bounce off, right? You might never able to, you might never be able to convert. You might just shoot off from your own wherever you actually were. If you move very slow, that's going to be moving so slow that it might actually never converge. Eventually it will, given enough capacity and time and computing resources, eventually it will converge, but it's quite possible that it's going to be so slow that it will be years before we see the results. So both are not good for us, so we don't want that, neither we want that. We want a particular LR rate at which we can travel slowly towards our, not slowly, but in an optimal rate towards our final minima. That is exactly what we're looking at. What dimensions we are talking about? Okay, so when you're asking questions, please make sure you're linking the context. The dimension was for the L-1 layer. I'm hoping you're talking about GradCam Guardian. Okay. So these are two things I wanted to realize whenever you look at the loss function. What are these two things? First thing is that this curve is not a fixed curve for all the times, right? The curve itself is going to change. So the curve is here right now, the curve might move here. In the next instant we are looking at, our weight might be there, and after some time our curve might actually shift at this particular point and your weight might be here. So your weight is actually trying to move on a moving curve, right? And that is why it is not a very simple way to, it is not simple to just draw our loss curve. The loss curves are drawn just by understanding at a particular moment. It is not going to be a fixed entity. So that's the first thing I want you to realize. Okay. Now the weight update. This is a very very important equation because this has so many things inside that it's wonderful that how people actually came up with this equation. Now mathematical gradient is a partial derivative. You can see that we have this partial derivative of the loss function with respect to the weight, and that's the weight we have. We use a negative gradient. This is the negative part where we convert our gradients to negative, and alpha is the learning rate. This is the alpha which we know about. Let's spend some time on this and understand that how things are working. Now, okay, now let's look at this equation. Now we should have written this is as t plus 1. So this is t plus 1 and this is t, right? And we're also, this is also t. Okay, now let's look at this equation. Now we saw that we have this input, it goes through two conv layers or multiple layers, this doesn't matter. And after that we have a prediction y, and we compare this with our target yt, and this somehow gives us a loss value. Now let's look at a particular parameter here, wt, right? In a particular kernel we have a particular parameter wt. Now kernel in our case, because in convolution this is different and this is different in fully connected layer, so I'm going to look at both. So this is our fully connected layer and this is our convolution layer. In convolution layer we're going to have many kernels, right? And all the kernels will have some value. Let's look at a particular kernel called wt1. wt1 happens to be t's time here, by the way. wt1 happens to be one of the weight of a kernel called k1, right? And this is going to be as 3 cross 3 cross 512, let's say, right? So we have many of them, so we're talking about this specific kernel, and we're talking about this specific weight, right? So that's the weight we're talking about. Cool. I'm hoping you realize what exactly we are discussing. So we have our kernels, we have many kernels, but we are looking at one specific kernel and we are looking at a one specific weight of that particular kernel, right? So that's the one we're talking about. Now let's look at the loss for us. Loss we saw some time back is proportional to all the weights we have. So it's going to be proportional to W1, this weight we're talking about, this weight, and this and this and this and this and this. So we have all the weights. So we have W1, W2, W3, W4 and so on. Now in our case we have let's say W512, sorry, we have W9, and this is going to be just one channel of the kernel we have, and like that we'll have 512. Please remember, multiply by 512 just to show you that we have many weights here, and these are not the same weights. Every single parameter, every single weight of your kernel is going to be different, so all 9 cross 512 weights are going to be different. Okay, so let me just simplify this. So our loss value is proportional to all the weights I have, and we are right now focusing on W1, and we have W2 and so on, right? It's dependent on all of them. Okay, now where exactly are we going with this? All right. Now, just as you saw in the grad cam, if a particular channel value, what is channel value? Channel value is the activation. How do we get activation? We get activation by multiplying the weight with the channel, the last channel, and that is what is going to give us a current channel. Now, in the grad cam, we saw that we can do something like this, where we have our prediction for a particular class. So let's write that, right? And our this is partial derivative, and we did a partial derivative with the channel pixel. So we had this, right? This is what we just covered in some time back. Now this gives us the correlation of our weight, correlation of our channel value with respect to the prediction we have, and this is how we can find positive and negative correlation, which meant that if this reduces, this is going to reduce, and if this increases, this is going to increase in case there is a positive correlation. In case of negative correlation, if this reduces, then this increases, right? And if this increases, then that is going to reduce, because we have a negative correlation in that case. Now how's this linked here? Now a similar principle we can apply for our weights also. What we can say is that if a weight is negatively correlated, which means if W1 increases, our prediction is going to reduce, right? Why? Because maybe this particular kernel was working for elephants, but the class which we want to predict is cat. Now in that case, if you increase the weight of a particular kernel which is working for elephant, and then you try and see what is the correlation with the cat, so of course going to be negative, because any randomly generated channel pixel in the initial layer which might come to this particular layer, this particular weight might multiply with that, and it's going to reduce the overall amplitude of the channel which we're going to create. So not only we can look at the relationship between the pixels with respect to class, we can also look at the relationship between the weights with respect to class, right? This is where the training comes in, this is where the grad cam comes in. That's why I covered grad cam for you first. Now let's look at it again, because it's a very important concept, but you might miss it. So let's look at it again. Okay, so what we're saying here is, I deleted. I hope you realize. Okay, so I'm just going to draw this dash to make sure that you realize this is the updated one. Okay, so what all have we discussed? We are saying is, what we're saying is that we have many kernels, right? And then we are looking at a specific kernel in last layer. It can be any layer, but right now we are looking at that. We have this kernel called K1. In the K1 kernel, we are looking at a specific weight, and this is the weight we are interested in. So what we can do is, first of all, we realize a loss function is dependent on all the weights. So I can write Wi, right? We are just right now looking at one weight, but it can be any weight on of any layer. So it is dependent on this particular weight. So I can do something like this. I can do a partial derivative of my loss with respect to this particular weight, right? Now if there is a positive correlation, that means that if this weight increases, my loss is going to reduce, right? Now this is different from what we covered in grad cam, so let me write both at the same time. Okay, first of all, let me write gradient ascent here, and then let me write descent here. This is ascent and this is descent. Now what is gradient ascent? Gradient ascent is, what is gradient descent? Gradient descent is that you want negative gradients to be there, and that is what is important for us. So you're looking for a negative correlation. And what is gradient descent? Gradient descent is that you're looking for a positive correlation. Now let's look at what exactly we mean. We mean what we want to say here is that if our partial derivative of the prediction with respect to partial derivative of a particular pixel, right? We want the pixel value to be positively correlated here. So what we want is that we want to see if increase the particular pixel value. So what if the activation of a particular channel increases, the probability of that class being predicted increases as well. So we are looking for a positive correlation here, right? Why? Because we are looking for a higher prediction value, right? That is why we are looking at this particular scenario. Now what is gradient descent? In gradient descent we are looking for a negative correlation. Let's see why. We're looking at the loss value, right? And we're comparing the loss value with respect to a particular weight. Now when the weight increases, and if this is the right weight and this is the right weight linked to the right class, we want the loss to reduce, right? So here we want the probability to increase, here we want the loss to reduce. That is why we're looking at gradient descent, right? I hope you realize that. So when we increase a particular weight and this is the right weight for the right class, in that case we want the loss to reduce, right? And what is loss? Loss is the prediction we are making and compared with the target we have. So if the prediction we're making is getting better, that is what we want, and the prediction is getting better because we are increasing the loss in the right direction. Let's say loss is increasing, sorry, the weight, we are changing the weight in the right direction. So let's say the weight is increasing and that's the right weight. That means a loss is going to reduce because that weight is linked to a particular class, right? That is what we're interested in. So we are looking for the negative correlation here. Now how this ties up is like this. Now let us say this particular weight, which is Wi or W1 in our case. Now this weight we have, so first let's look at the equation. Let's say we have L equal to, we are going to keep the equation simple just so that we can understand this. So our equation is going to be xi into wi plus x2 into w2 plus so on. Let's say that's the equation we have. It's going to be a very complicated equation because we have a kernel, so one weight is going to multiply with many pixels. Now if you think about that, we have to take a mean every time we are doing this, so we can't just, I can't just write an equation. So it's a very simple equation we are writing. So, and let's say we have only one time, we are only multiplying this one time. Now we are interested in the relationship between the L and the W1 here, which means that we are trying to calculate the derivative of L with respect to W. Now let us say we do that. So we do a derivative of L with respect to W1. Now this left hand side is fine, but let's look at what happens on the right hand side. Now dxi with dwi is 0. Why is that 0? Because this is the input, xi is the input, so the weight has no control over the input. Input is always going to be constant for a particular layer, so we don't have any control directly there. So that's not a problem for us. It's going to act like a constant, so we can take our xi at front, and derivative of differentiation of wi with respect to wi is 1 in this particular case. So that's not a problem, right? We are talking about differentiation here, not a derivative, partial derivative. But this is constant, perfectly fine. But now we are stuck at something like this. We have to calculate the derivative of dw2 with respect to derivative of dw1 plus derivative of dw3 derivative of w1 plus so on. You see that if we take derivatives, we'll have to calculate these guys also, and that is something which is very difficult because we may have millions of parameters, and a loss equation is going to depend on the millions of weights we have, which means if we take a differentiation, we have to calculate the derivative of every single weight with respect to the weight we are interested in, and that is very difficult. We can't handle that. So mathematicians have a very small trick instead of this. So instead of calculating a differentiation, we take a partial derivative. Now there's a difference in derivatives and partial derivatives. In derivative, we take our we assume that these are not constant, so w2 is not constant, w3 is not constant. But in partial derivatives, when we calculate something like this, what we can say is that this remains same again. So we still have xi here because partial derivative of w1 with respect to w1 is going to be 1. So this is 1. They both are equal. But in this specific case, x2 and partial derivative of w2 with respect to partial derivative of w1, this is 0. And this is 0 because in partial derivatives we say that they're very small. What we say is that this change is so small, or the change in w1, finally we're calculating w1, right? W dash or w1, the final change in w1 is going to be so small that it's not going to affect anyone, right? That's the trick we have. We say that this w1 is so small, or this change is so small that they're very small, because of which we can assume that to be constant. How should we wrap our head around this? What we're saying is that, let's say our loss equal to, let's not look at loss, let's look at some other equation. Let's say we have this k is equals to m plus n, right? So let's say that k is equal to 3 and m equal to 2 plus n equal to 1. That's the kind of equation we have. So what we're saying is that we are going to change this m so small, which means that we are going to say something like this. You can say that that's not true, but that's the idea of partial derivatives, that we are changing a variable so small that we can actually consider these guys as constant. Even after changing that, we don't have any changes on the other parameters. So that is what we're going to do. So we're going to take partial derivatives, right? This what is the reason behind partial derivatives? When we take partial derivatives, we can assume all of these guys are constant and we can just get rid of them. So our equation becomes very simple in terms of the calculation. So that's the idea behind partial derivatives. Okay, now let's go back to our equation and see how it's linked back to our main equation. Okay, so where were we? We were here. We were saying that we are considering this particular kernel, and this kernel has 3 cross 3 cross 512. We are going to consider only this particular weight, and let's call this weight W1. All the other weights are considered to be constant for this backprop, right? But I'm saying this backprop, which means you have to do a backprop for W1, you have to do a backprop for W2, you have to do a backprop for W3 and 4 and 5 and 6 and 7. Which means if you have 1 million parameter, you have to do backpropagation for 1 million parameters, right? All of this happens seamlessly because that is what is the target task of PyTorch or TensorFlow or Keras. But that is what is happening in the background. So we are doing the partial derivative of each one of these guys, and when we do a partial derivative with respect to W1, we assume that all of the other guys are constant. Otherwise we can't just solve it. Mathematically this is okay because we are saying that they tend to 0, which is what is able to help us satisfy the equation. And I'll come back to this, that why this is required. Let's say we are able to figure out the partial derivative of W2, derivative of W2 with respect to W1, derivative of W3 with respect to W1. Let's say somehow we know that. Why is still not a good idea to go in that particular route? So but let's hold on to that particular question for a moment. Now let's come back to this particular equation. Okay. Now let's look at our partial derivative again. So we are saying that we have something like this. Now first of all, realize that we are talking about loss. We are not talking about prediction. In case of prediction, we want to have a positive correlation with W, but in case of loss, we want to have a negative correlation with W. What is negative correlation? That means that if we change W, we want the L to be changed in the opposite direction, right? We want to change W in a direction which is good for us, right, or the good for the function or your model. But when we do that, we want the loss to be changing in the opposite direction. That is what we are interested in. I hope you realize this is what we want, right? And I'm saying we change W, we are not saying we increase W, because maybe the W has to be in the negative side, maybe the W has to become small. So that is something which we want, and we're not sure that it needs to be negative or positive, and we allow our equation to figure that out. So we're going to look at both the scenarios. Okay, now in this particular case, let's say we have this L and we have this W. Okay, and we are going to write the partial derivative of L with respect to partial derivative of W here. Let us say our weight was 4. Right, if the weight was 4, our loss was, let's say, actually you know what, we can actually create a simple table for this and we can write an equation for that. So let us say the y equals to x squared, or we can keep it even simple. Yeah, so let's say y is equals to m, we don't want m, we want w into x plus c. Right, very simple equation. Now what we are interested in is to solve this particular equation. We want y to be 4 and x we have given as 2. We want to figure out what w is, and we have this plus c, right? And of course you can see that c is going to be 0, and we can write it 0 or partial derivatives again constant, so it doesn't matter. But that's the equation, let's say we want to solve, and w right now is 1, right? So we are here. Okay, so our w, let us keep this, c is going to be 0, so let me just throw it out. So let's say this is the equation we have. So 4 equal to 1.2, 1 into 2, of course is not true, but that is also not 4. What is this? This is the prediction we have, so we are going to write this as wt. Okay, what we're saying is our loss right now, and let's keep our loss to L1 only. Loss right now is the prediction I want, which is 4 minus the prediction which we are currently predicting, and that is equals to 2. So our loss right now is equals to 2, and our w is equals to 1 in this specific case, right? Now I'm going to make a table and let's see how that table helps. So we have a loss value here, we have a w value here, right? And we may just fall off the loop. So let's write our w prediction, and our loss, our value of w, and then delta derivative of loss with respect to derivative of w. Let's say we have something like this. Okay, now y is what? 4. Y dash is what right now? 2. Loss is what right now? 2, right? And weight is what right now? 1, right? This is what we have. Now we need to calculate this. Okay, now this, if we see our equation, and if we go back to our equation, which is this equation, right? So our equation right now is it can come from the equation also, but I want to do it manually as well. So we have, so this is y, right? So we are saying basically 4 minus y is a loss, which means a loss is equals to 4 minus w into x. C, let's say it's 0, so a loss is equals to 4 minus x, we said is 2 into w, right? So you can directly see here that the partial derivative of wl by delta w is equals to minus 2, right? It's very clear here, but we don't want to use the equation because we will not have that kind of freedom in our deep neural network. Our equations are going to be very complex. So let's say what actually what can we actually do now. If you see here that if I increase our w slightly on the positive side, which means I make my 1.0 something, right? In that case, this is going to increase. If this is going to increase, then the difference, this is going to increase, right? So 2 is going to become 2.0004. When that happens, 4 minus 2.004 becomes a smaller value as compared to 4 minus 2, which means loss reduces, right? So I hope you realize that, right? I hope you realize from these two equations that if I increase my w, the w into 2 is going to increase, which means our prediction is going to be closer to 4, which means 4 minus this new number is going to be a smaller number, so loss is going to reduce, which means right now our delta w, if we keep it positive, right, our delta L is going to be negative, right? I hope you understand this particular part. I'm going to link it back to exactly what we mean, so you don't have any worry with that. So if you see what we want right now, okay, what we want right now is let's say, how do I write what we want? Let me write a question mark. Right, question mark is what we want right now, what we want for w right now. Right now w, if we increase w, our loss is going to reduce, right? So we want to increase our w right now, so I'm going to write an up arrow for this. Right now from the equation you can see that delta w by delta L, partial derivative of L with respect to partial derivative of w is 2, so we know that. So this value is equals to minus 2 right now. We saw this from the equation also, right? And even if we calculate that through the numerical analysis of our model, we are going to get this value also. So we have this minus 2. Now how should we update our w if this is minus 2? That is very important. So we have the equation of w, which is equal to w equal to w, which is old one, minus the partial derivative value, which is this value, right? Which means that our new w dash is equals to old w, which is 2, minus outside, and inside we have this minus 2, right? That's the equation we have, and soon this relationship of minus is going to become very clear to you. So which means our w is going to be equal to 4, right? So that's the new w we have. Now let's look at our equation again. This is our equation. Now in this case, remember that w is going to be 4, so we are going to use w equal to 4 for our use, right? And soon you're going to realize that why do we actually have our learning rate parameter. Now let's look at the second set of equation, the second time, right? We just did a backprop, this is the backprop we did, and now we have a second step. In second step we have, this is not going to change because that's the prediction we have. Let's see what is this now. Now if w is equals to 2 now, right, this 2 into 2 is going to be 4, and our loss is 0. So this is here, this is here, right? And that's the result we were interested in. And our weight right now is equals to what? W, am I doing a mistake? I think I'm doing a mistake. Okay, so our w dash is equals to w old, which is 1 plus minus, yeah, I did a mistake. Okay, so w is equals to 3, not 4. Okay, so let's calculate our y again. So if w is equals to 3, that means that 3 into 2 is 6, so our prediction becomes 6, so this becomes 6. And if you see loss right now, our loss right now is going to become what? we see loss is 4 minus 6, which is going to be equal to minus 2, right? This is very interesting. See what will happen now. Our weight right now is 3, and now let's look at a derivative again. Now if you realize, if you calculate the derivative again, it's again going to become minus 2, right? But what do we do? So this is from this guy, but what do we want to do actually? What exactly do we want to do? So if you see, let me draw the W curve. Now this is the W axis. Right now when we started, the W was at 1, so let us say this is 0, this is 1, 2, 3, 4, and so on. And where exactly we want to be at? If we see this equation, we want W to be 2, which means that we want to be here, right? But where exactly are we starting? We are starting at this point. We started at W equal to 1, right? And in the next update, when we updated this guy, we updated by 2, right? That's the 2 update, which we minus 2 update which is going in, which means that we actually went here. Now if you realize, we made this axis here, right? This axis is what, that we wanted to increase it, but we increase a lot right now, so we went to 3 here. Now here you can see the graph, and you yourself can say that now we want to reduce it, right? So if we see our equation has automatically that inbuilt. Remember, this is the W, this is what we are going to get, right? This is what we have. So if you see our equation again, which is the loss equation. What was the loss equation? Loss equation was 4 minus y prediction, which equals to 4 minus this guy, which is W into 2. Constant is gone already, right? That is what we have. This is the loss equation we have. Now loss, when we have increased our W, right? We increase our W, our loss has increased, right? This equation is directly telling us that, which means that once we reach here, we actually want to reduce, right? Okay, now let's look at the partial derivative equation again. So W dash equals to W minus the partial derivative of WL with respect to delta W. Right? That's the equation we have. We are again seeing this equation, and I'm not using alpha just to show that why alpha is actually required. Now what is happening is, now when we increase our delta W, our loss is increasing, right? Why is that? Because you see, we are at this particular point, we are at W equal to 3. If I increase my delta W, or which means if I increase W here, my loss is going to increase, right? Because we are going to go farther away from the point 2 where we want to be. So this is positive right now. So if we just rub this, so this is positive right now. If this is positive, then we have the negative outside, which means whatever we have inside as positive is going to become negative, which means that automatically what you're going to calculate now is going to reduce the weight for us, right? That is the importance of this negative equation. And so this time we want to do what? We want to reduce this exactly. So this came as positive in the last step. This is going to come as negative in the current step, because we are going to look at with respect to the loss value, right? So, and unfortunately, because we're not using any alpha, the update is still going to be with minus 2 here, which means that the update right now was plus 2, which is going to go in, which means that whatever weight we had what, W equal to 3, we have this minus outside, and this is going to be positive 2 now. So we have this 2, which means we are going to go back to 1, right? So from 3 we are going to go back to 1, and again at 1 we are going to be at this state, which means we are going to go back to 3, and again at this state we are going to go back to 1, and so on. So you see, we are going to get stuck in this particular cyclic loop, because we are never able to stop at this particular point. Now this is very much linked to our initial comment that you want to move slowly so you can reach and stop at a particular point. Now this is very similar to another scenario. Let us say this is your house and this is your car, and your car can only travel 5 feet at minimum, which means, and let's say you were 2.5 feet away from your house, which means you're going to go 2.5 feet ahead of your house. Then when you take a back U-turn, you can only going to go 2.5 feet, 5 feet again, and this is again going to be 2.5 feet. So you're just going to oscillate around your house, and you're never going to reach your house. This is what you saw when you are training your curves also, when you're training models also. Your model trains properly, but at a specific after specific point it just shuffles, right? And it is shuffling because it's not able to stabilize and get to a particular point and just keeps on shuffling. And what is the solution to solve particular this solution is going to be reducing the learning rate, and that is what we're going to look at. But I hope that you got the idea about what w1 and other guys are. So let me still cover that again just to make sure that you get exactly what we're discussing, right? And this time we are not going to look at equation, we are going to directly look at a particular value. Now again, our let's say we have L here, or let me take an equation again, because I think equation would be easier for you to understand. But let me change my equation this time. Let's say the y is equals to x into w, and that's all, right? C we are just not focusing on. Now let us say the y was supposed to be 6. This is what we are interested in. In fact 4 was a better number. We're still going to go for 4. So y dash, which we want to predict, is 4, and w right now is equal to 1. So I'm going to write the whole thing so you realize this. And loss is equals to 4 minus x into w, and let's say we are this time looking at square loss. Okay, so this is what we have. So let me write the stuff first so we don't get confused. So this y dash, what we want to predict, this is the value of w right now. This x is equal to 2, so we don't need to worry about that. Okay, so y dash is 4, v is 1, and what is y we are going to predict? If w equal to 1 and x equal to 2, that seems like 4 minus 2 is what we are interested in, y right now. Okay, so this is our y. So 2 into 1 is going to be 2, right? And a loss which equal to y minus y dash. Okay, this is y dash and this is y. Our loss is equal to 4 minus 2 right now, right? 4 minus 2 is equals to 2, right? Other we are going to seize, so don't worry on that. And this is the first case. Now second case, let's say we are at y, this is constant, so not a problem. Remember, we are going to get an update of x, because x is equal to 2, we are going to get a derivative of 2. So let's say we updated this by 2, so our w became 3. If w became 3, our y is going to become, sorry, we have a square also. You guys are not here, I'm not able to, I'm all alone today. Okay, so loss is going to be what? So this is 4, this is 2, 4 minus 2 is 2, 2 square is 4. Okay, this time we are at 4, this is constant. Our w is 3, which means 4 minus 2 into 3 6. 4 minus 2 is 2, and 2 square, this is what again? This is 6, but 4 minus 6 is minus 2, and minus 2 whole square is 4, right? You're going to see that we will not be able to do and come out from this. Okay, now let's see this equation, delta L by delta W. Now delta L by delta W, if you see this guy, that is going to be partial derivative of L with respect to partial derivative of W. If you realize that we have a this is square, 4 is constant, so we can just get rid of that. And or let's solve the equation. So we have 16 plus x square w square minus 8xw. If you take a partial derivative of this, you're going to get 2 into x square into w minus 8 into w. So that is the equation you will have to solve if you're looking at a square loss, right? And that is why we were looking at a very simple loss earlier on. But let's say this gives us some value. Now x, this is again a constant. Am I missing something? 8x, sorry, yeah. So x is equals to 2, we discussed. So this is equals to 4 into 2, which is 8 into w minus 8 into x, and this is 8 into x. X is equal to 2 again. So this is equal to 8w minus 16. That is the derivative we have, right? This is the derivative right now, because we have a direction fixed here already. Okay. So if w, okay, so this is equals to 8w minus 16. Now if w is equals to 1, if w equal to 1, we have 8 minus 16, which is minus 8, right? Which means the derivative is actually negative. Derivative is negative. Let's look at a w update. W update is equals to w minus this value, right? which means the negative of negative is what we are going to add. Negative or negative is positive, which means we want W to increase, and that is what we see here, right? Our W equal to 1, but we know if we want to solve this equation, our W needs to be 2, and that is directly coming from the equation. So this is negative here. Now let's look at the other case where our W becomes 3. If W becomes 3, 3 into 8 is 24. 24 minus 16 is 8. It is positive, which means this is positive. Why is this positive? Because our loss has now increased, it's gone on the other side, right? And if you again go back to a curve where W started, this is W 0, 1, 2 and 3, this way we want to stop. But when we were here, our equation is telling us, right, we are going to get a negative here. Our equation is telling us that increase that. So we increase it, but because we don't have a learning rate parameter, we are just increasing it to a very big value, and we ended up at 3. When we are at 3, our equation automatically is telling us that this time our delta L by delta W is positive, which means when you are increasing, it is loss is also increasing. There's a positive correlation. We don't want that, and we convert that into negative outside. So the positive value now becomes negative, and so from here we jump back to some smaller value. But because we are not taking into consideration any alpha parameter, we are not able to limit that, and that is the reason why we have this learning rate. Our W was increasing by plus or minus 2, right? We want to stop at 2, but we were at 1, and when we keep on jumping from plus 2 to minus 2, we either jump to 3 or we come back to 2. But if I had an alpha which was 0.5, I would have precisely stopped here, and that's the loss, where the loss value would be 0. But finding the exact alpha is very difficult. First thing. Second thing, this alpha for this W is 0.5 right now, but what if the equation was W1 plus something into W2 plus something in W4, which is what we have, which means we have to calculate this alpha for every single parameter in our network, which means that if I have 1 million parameters, I'll have 1 million alphas, right? And that is a nightmare. So that is something we can't do, or we can, but I'm going to show you that why we still don't do it. So let's look at the equation again. W dash, which is going to be the new weight update, is going to be equal to the old W minus, because we want the negative correlation with respect to the weight, derivative of loss with respect to the derivative of partial derivative of a W. That's the relationship we have. And what this equation is saying essentially is that if increasing delta W reduces loss, right? So this is the axis we have, right? We want to keep on doing it. And if increasing delta W increases loss, we want to reduce it, and that is the reason why we have the negative part, right? So let's look at this part again, because this is very important. Rest of the content is easy, we can cover that. Is it why the loss goes up and down during the last few parts? That is correct, Prasad. Is squared loss right? Squared loss. This was wrong when I was explaining, but then I made it correct. Please write full questions. Okay, so let's look at what exactly are we looking at. Why is this negative required? Because we're looking at a negative correlation, right? Which means that if delta L by delta W is negative, think about it and don't even look at the equation and just talk to me, okay? You have increased your W. Increasing your W has reduced your loss, right? What do you want to do now? You want to increase W further, right? That is what you want, right? So let's see what we are saying. We have taken our W and we have increased our W. Increasing our W is reducing our loss. What do we want to keep on doing? Let's say this is the next time. We want to keep on increasing our W. That is what we want. Okay, now let's look at another scenario. We have increased the W, but that has reduced the loss. That has increased the loss. We have increased our W and that has increased the loss. What do we want to do now? We don't want to increase, we want to reduce. We want to do exactly opposite of what we did last time. So we want our W to be smaller as compared to what we were doing, right? Now this is on the increase part. Let's say reduction part. Your weight has reduced, so my weight has reduced, but the loss has increased. My weight has reduced, but the loss has increased. What do I want to do? I don't want to reduce my weight. I want to increase my weight now, which means I am looking to increase my weight. Now, in this equation, in this last part, our weight has reduced. We have reduced the weight, and the loss has also reduced. What do we want to do now? We want to keep on reducing it. So we want to capture this. We want to capture these 4 different possible combinations. So how do we do that? Let's see how do we do that. So now let's look at this. This is delta L partial. Let me say delta. It's partial derivative is very long to keep on saying. So let's say this delta L by delta W. Now this from this is clear is negative, right? Let's first look at this part only. Now this delta L by delta W is positive. This is negative. I'm hoping you realize why is this negative. Why is this negative? Delta L is positive, right? Loss has increased. Delta L is negative and delta W is negative. So positive divided by negative is negative. That is why this is negative. And this is what? Negative divided by negative. So this is again positive, right? Just to make sure that all of you are following, let me directly write this. My surface is heating up. So we have positive divided by positive. Here we have positive divided by positive. Okay, I've done a mistake again. Okay, so our negative divided by positive, right? That is what we have, negative divided by positive. Here we have positive divided by positive. Here we have positive divided by negative, and here we have negative divided by negative. So let's solve this. This becomes negative, this becomes positive, this becomes negative, this becomes positive. This is cool. Okay, now let's see, we want to increase it. Okay, which means that this term, see, this is this term, right? What do we do here? We increase the weight and that reduce the loss. So we want to keep on increasing it, which means I want to change the sign of this guy, which means I want to multiply this with a negative number, right? If I multiply this with negative number, I'm going to switch it. I'm going to increase it now, right? Because I'm not going to subtract this, because this is going to come as negative. Negative and negative is going to become positive, and I will be able to increase my W. That is what has happened here. Let's see what has happened here. Now this thing was positive, and that our weight increased, our loss increased. What we want to do now? We want to reduce it. But what is this now? Positive, which means that we are going to further reduce it automatically, which means that this will go as positive here, right? So we have this negative. You realize what is happening? This negative goes inside this and automatically becomes positive, right? I don't have to multiply it with anything. So let me just remove this guy. Let's look at it again, okay? Okay, now when our weight increased, our loss reduced, which means this came as negative, which means we want to keep on increasing our weight, which means if this negative automatically goes inside, it's going to become positive because of this guy, right? And our weight is going to increase automatically. Perfect. Now let's see the second case. Our weight increased, because of which our loss also increased. Now I want to reduce it, right? But I can't multiply automatically. I don't want to forcefully multiply this. But let's see what happens. This time we have this positive number, and the positive number goes in. Because the positive number is going in, we have the negative outside. So this positive update will be subtracted from W, which means W is automatically going to come down. Right? This is happening automatically now. Now let's see what happens in this case. In this case, I reduced my weight and my loss increased. I reduced my weight, so my loss increased. So what do I want to do? I want to increase my weight, because reducing weight is increasing my loss, so I want to increase my weight. So this came as negative, and this is negative, and when negative goes inside, it automatically becomes positive because of this guy. And let's look at last case, where a loss, our weight reduced and a loss also reduced, which means I want to keep on reducing. So let's see this happens automatically or not. So we have this positive now. This positive goes inside and automatically becomes negative. That is why that negative sign in front of that partial derivative is very, very important. It automatically handles the direction in which we want to reduce. Right? Your derivative is going to tell us what is the current relationship between the loss and a W, and that negative sign is going to handle whether we want to increase the weight or reduce the weight automatically. So that is very, very important. And you also realize the importance of alpha, that if we don't control that alpha properly, then either we are going to increase our weight by a large value, or we're going to reduce our weight by a large value, and we'll never be able to come to that specific point where we want to stop. Right? And this is what you see in your last few epochs also. It keeps on going up and down. There's one more thing I want to share with you, and that is very fascinating. Let us say we want to be at a number, or our weight want to be at a number 0 0.3, 4, 5, 6, 7, and 8 and 9. Let's say our weight wants to stop here. Now let us say the you saw the equation, right? In the equation, the derivative of L with respect to derivative of W was 2, which was constant. Let's say we have a very simple equation like that, which means our derivative is 2, right? Now, and let's say our alpha is 0.5. We have picked 0.5 in that specific case. Let's pick a small number. Let's say the our alpha is 0.01. Okay, 2 into 0.01 is 0.02. 2 into 0.01 is equal to 0.02, which means in the equation W equal to W minus this thing now, right? So that's we have already done, right? This is the delta L by delta W, and this is alpha. So that thing is going to come in. But based on the direction you are, this sign is going to automatically be either negative or positive, as we saw, right? Assuming we have a very simple curve. Now, by the way, the equation which we saw earlier, the gradient of that equation is going to look like that. So it's just going to shuffle. It's going to be exactly same on the opposite side, but that is not true for our equations. Our equations are going to look very different, right? Our curves are very different. Our function is very complicated. So, but let's say this is the case because we're just discussing this, which means that is the update I can do. Which means if I start at a very small value, let's say because of the random initialization, I'm starting at something like this. Right, if I start at something like this, we can immediately see that the weight is positive and we are at a very small value, so we want to go in the positive direction, right? So this is going to be we are going to add this multiple times to this, but realize that how many times we have to add this. We are at 3, 4, 5, 6, right? And this is 0.02, which means we are talking about this kind of update where we can update the second decimal value, but we have a very big decimal value in the first one itself. So how many times I have to update to get to 0.34? That will be easy. 34 divided by 2, that's 17. So after 17 updates, I'm going to be at 0.34000, and then I've done how many updates? I've done 17 updates. So this is also going to change. So let me still not calculate that. Let's say this is 3, 4, or 17, something like that. We have this kind of number, right? That's where we are. Perfect. Now, what about this digit? I can never fix that digit now. Why can't I ever fix that digit? Because my updates are always going to be in 0.02, because I'm using a fixed learning rate, which means my next update is going to make this 0.34 into 36. And next update is going to make this 0.34 again. You see, I can never fix this digit because my updates are coming at the rate of 0.02. The only way I can fix this digit 5 now is by reducing my learning rate, and that is why you see that we reduce our learning rate 10 times every step, because you are trying to fix the least significant digits now, which means that if my learning rate was not 0.01 but somehow I'm able to change my learning rate by 0.001, but how do I know that I have to change my learning rate, right? And that is why we are going to use something called LR finder. Now when you run your curve, you're going to see that you hit a stable point. Here we say that we have hit a kind of plateau. But if you zoom in, you're going to see that you're actually struggling, something like that. But if you zoom out, it's going to be a flat road, right? Same as road. So when we hit this kind of issue where we are basically shuffling between two specific points, we say where we hit a kind of plateau. We are not able to move out. There's not a plateau we are going to discuss today, but let's say we have hit this kind of local minimum. The moment we do that, we reduce our learning rate by 10 times, and now I can fix my fifth digit, right? I can fix my third decimal point. And even after this, this is how your curve is going to look like, and so on. What have we done here? We have reduced our learning by 10. What have we done here? I had done fixing this. I have reduced my learning rate 10 times again, so I can fix that. Then we reduce our learning rate again. I can fix that, and so on. So that is exactly how we are going to handle our learning rates. I hope you are with me on this. I'm going to wait for 2 minutes and then take questions and then move forward. The loss curve is changing every batch epoch. It means minima of loss curve is also changing. Yes, your minima is always changing. Your minima is dependent on many millions of parameters, right? So it will keep on changing. So that is why it's very difficult to even realize that exactly how the loss curve is going to look like. So whenever you see online any loss curve, it's an instant of that loss curve. The next moment you run the equation to draw the loss curve again, it's going to look very different. But because every parameter is moving in the right direction, we have fortunately a system where we are going to hit minima, and this might be not be the global minima, but it will be some minima. I was wondering if there's local minima and local maxima concept here also. If yes, then how can we deal with it? We don't have any concept of local maxima here. Local maxima I was showing you with respect to GradCam. Please forget that for today's session. We only have local minima, right? We don't get stuck at local maximas because we're going to see soon why we don't stuck there. But local minima we can get stuck, and we have to figure out a way in which we can get out of our local minimas. So I'm going to wait for 2-3 minutes before we move out from this equation. So please ask some questions. By the way, we are also moving to something else because now since everyone is online, I actually want to have a proper interaction with you. You see, I'm a person who needs people to talk, and right now, unfortunately, not the Deepak is also not there, right? So I feel alone without you guys. So I think we are going to come up with a system where we can do live conferencing. I will try Cisco or Zoom as well. Zoom is not reliable. I don't have a good option for that. I've tried Google Meet also. That is also very weird because every time you're going to join, I have to basically allow you to join. So that is not instant. Cisco might work. So in a couple of days, I'm going to try it out. What is the best strategy? And Sunday's session is going to be on some system like that where you can speak or you can basically the interaction is going to be live. It's not going to have this kind of YouTube delay. All right. I hope you don't have any questions on that. And let me see where you are. Oh, you're quite back. Okay. As you can see, there's a delay, right? Okay. So this was, I believe, 5 minutes back. There's close to 5 minute delay. Okay. Let me proceed. But keep posting your questions. I'm going to come back and look at the question and go back again. So don't worry on that. Okay. Mathematically, gradient is a partial derivative of the loss function with respect to the weight. That is what we're seeing. We use the negative gradient because we want to do exactly the opposite of how our relationship between the loss and the weight is right now. I like you to think about that because I just drew that equation and showed it to you. But I want you to realize this that if my weight is increasing and my loss is reducing, that's a good thing. I want to keep on doing that. But delta L is not negative and delta W is positive. So we have a negative inside. But I want to increase my W. So there has to be a negative outside. So I want you to think like this. So this equation of weight update becomes very clear to you, right? The alpha is something we are not going to talk about because that is the session for this alpha. Now, constant learning rate algorithm. Now, this is what we have been using till now. This is what we have been using till now, which means that our alpha is not changing. Which means when you set your SGD alpha 0.1, it's going to be 0.01 or 0.1, whatever you're going to set for the rest of the program. Now, this neta is called the learning rate. It's a hyperparameter, and we have to find it. Right? We're going to see how exactly we find it also. You're changing LR every 10 epoch, a standard practice. Just an example. We don't change it. We don't change it every 10 epoch. I'm going to discuss that how do we actually change. And okay, so this is a constant learning algorithms where we have just one single alpha fixed, and then we basically add something called momentum also, but we're going to cover this like 5-10 minutes from here. Now because this question is here, I'm going to answer that. Okay, now we have this learning rate right now, and let's say we change our learning rate after 10 epochs, and we say our learning rate after 10 epochs is 1/10 of what we have. I'm trying to use it curves today. Okay, this is, let's say, 0.01. So this is our learning rate, and let's say after 10 epochs we reduce it, and then we say our learning rate is 0.001, and after 10 epochs we further reduce it, and this becomes 0.0001, and then we reduce it, and then we reduce it. It is a step function, and this is on the log scale. Now when you do something like this, I want to show you my favorite image. Where's that? Yeah, okay. I should actually bookmark this because we use it so much. Okay. Now, when you do this, right? Basically, you're saying this, that you know that it needs to be reduced after 10 epochs. No one knows that it has to be reduced after 10 epochs. And again, it is going to be different from different problems, because let's say we are using face recognition as a problem where we have 10 million faces and we want to learn them. No way in 10 epochs are going to be close to the kind of accuracy you want where you can fix something, right? In fact, in our equation also, when we were writing, we realized that we wanted to be at 0.34567, right? And let us say our equation, y equals to x into w, right? That is what we had. Let's say the x was 1. If the x was 1, in fact, if let's say x is 2 only, right? So x is 2 and w we want to calculate, and our learning rate we use as 0.01, which means we are going to multiply this with 0.01, which means we have updates of 0.02. Even in this case, we are going to take 17 epochs to change this, right? Because at least 17 steps are going to be required to change this, because we are going to look at, and let's say one image is one epoch for us, right? So, and we have a batch, so every time it has to change, okay? So which means that I have to change, I have to update my weight parameter 17 times just to reach here. So there's no guarantee that in 10 you can do that. You will have to take many more steps before you can actually arrive at that particular point. Now, if you had done only 10 updates, which means you were at 0. You were at 0. If you multiply this by 10, what do you get? 0.20, right? But we wanted to be here. Now you reduce your learning rate. What does that mean? That I have now made my updates as 0.002, which means that I am going to take now 100 steps before I can take this to some other digit, right? So you're unnecessarily slowing down. So what is this step exactly? How do we know that we have to change our learning rate? This is exactly what I was telling you, that when we are going to train, we are going to find this point, right? This is in Keras there's a function called reduce LR on plateau. So reduce LR on plateau. Basically, when you hit a kind of plateau, you reduce LR. Basically, now you can. So this becomes an automatic update. This is what we would be interested in, and this is what we will be doing. Okay, what if the loss is not affected in the same proportion by different weights? Loss will definitely not be affected by different, will not be affected by the same proportion by different weights. Of course, it will not be. So I don't understand the question. Every weight is going to take its own time, right? And based on where the parameters initialize, it's going to take its own due time. And that is why when you are training your parameters after the first epoch, if you check the class accuracies, it's not going to be the same. For one, it's going to be high. For others, it's going to be small, right? And that is the reason we are looking at here. And when we slowly train our network, all the weights are not going to be coming at the same speed. Imagine that we have 10 cars and these cars need to arrive at the final point. Not all of them are going to come at the same speed. So some weights are going to be getting faster there, but because they're going faster there, the updates also need to become smaller for them, right? But here we are saying that we are not able to control all the weights. So there are two approaches, and that is what we are covering in the session right now. The first approach is that we have the constant learning algorithm, which means this neta is constant. Second is what we're discussing right now is the adaptive learning algorithm, which is what we just discussed. Now, in the adaptive learning rate, we have AdaGrad, AdaDelta, RMS Prop, ADAM, and many others. Right? What is the difference? In the constant learning rate algorithm, this neta is constant for every single parameter, right? And that is what is the question what Shashank is also trying to ask, that what if the proportion in which the weights are affecting the loss is different. Now in case of neta, you will think that because my weight update, because my learning rate is fixed for every single parameter, I don't have that kind of freedom in which I can move some parameter fast and move some parameter slow, right? So that sounds like a negative thing, and we're going to see it's not actually. But we have another kind of algorithms also, which is adaptive learning algorithm, where every single parameter which will have its own alpha, right? So this sounds like a good plan, where we have Adam, Adagrad, and that is what we see people online using also, where I can change every single weight differently. So every weight will have its own parent, its own alpha, its own way of managing through that loss complex curve we have. So we're going to discuss that. So having the same alpha for different weight may not be correct. That's what I'm going to say. That's what I'm telling you, that having the same alpha for different weight will be a good idea in due course of time. Let's see, let's progress for that. Let's proceed for that. Okay, so the top three. Now these are the top three you need to look at, and that's all. Why we are going to look at these top three? We're going to discuss that. So we have gradient descent. Gradient descent is something you are using right now. Now gradient descent calculates the gradient for the whole data sets in updated direction opposite to the gradient until we find the local minimum, right? So gradient descent is actually what we want. Gradient descent means that we calculate a gradient for every single image in our data set and then calculate one particular step and take that step. Now this may not be feasible because my face recognition data set might be 10 million images. My network has to go through 10 million images just for one update. Not a good idea. So we have something called stochastic gradient descent. But unfortunately, stochastic gradient descent means that I have to go through one image once and then update, then second image one, then update, third image one and update, fourth image once and update. We can't do that either because then I have to do this 10 million times, and every time I just take one image, I'm not learning from all the images. So we have something in between. We don't use pure HGD, we don't use pure gradient descent, we use something called mini batch gradient descent. What is mini batch gradient descent? In mini batch gradient descent, I do stochastic gradient descent, one image, but we actually have 32 images, and I do the 32 checks. I go through these 32 images separately, but take a mean or average of these gradients and then update back. That is what we actually do, right? So if you ever get in a fight with a mathematician who's saying that you're not using HGD, just say yes, I'm not using HGD. We are using mini batch gradient descent, right? So HGD or stochastic gradient descent means one update, right? Gradient descent means going through all the images at once.
Go ahead.
My Siri is interested. Okay, so gradient descent means going through all the images at once and then doing a backprop. Stochastic gradient descent means going through one image at one time and then doing a backprop, which means I'll have to do 10 million backprops just for one image, just for one epoch. I don't like that either. So we do something called mini batch gradient descent, where we do stochastic gradient descent, but slightly differently. We lie basically to stochastic guy that we're going to go into one image. We take a batch of 32, which means I'm going to pick a batch of 32. Remember, in this batch, I have to make sure that all the classes have equal or equalist representation. You might say that in ImageNet I have 1000 images. I can't pick a batch of 1000. You're right there. So what we do, we pick up a big batch still, let's say 120 or 256, and we hope that in four batches or 10 batches, I'm able to cover nearly every single class, and that should be the idea. Your batch size should be able to cover all the classes as soon as possible. Going through 10 batch size of 10 for ImageNet, where you have 1000 classes, is a very bad idea, right? So that's what gradient descent or stochastic gradient descent is. Autograd is more preferable for sparse data. Please realize that, right? First of all, let me clear out exactly what is going to happen. So whatever text is there, you can start understanding it. Now, Shashank also said that it makes sense to have different alphas for different weights because all of them are going to behave differently. What I'm telling you, no, that is not true. There are many other algorithms apart from HGD. HGD is what? We have only one alpha for every single parameter. Sounds like a bad idea. But this is again very similar to what we do with ReLU and what we do with our ResNet, where we take a stride of 2, even though we know that taking a stride of 2 is actually going to reduce a performance, right? And then we say what? If it is not going to reduce performance, because whatever computation benefit we have, we add it back as the parameters. Same thing is going to happen in gradient descent soon. We are going to cover that. So first of all, keep these two ideas in mind, that gradient descent, one alpha for every single parameter. All the other algorithms, right? Except gradient descent with Nesterov. So we have Adam, Adagrad, Arbuz, Adadelta, all of them. There we have a different alpha for different weight, right? That's the other part. So we have two worlds, world A and world B. We are going to use the world A where we have only one alpha for every single parameter, and we're going to discuss why that actually makes sense soon, okay? But on the other side, we have Adagrad and Adam, where we are going to have different alphas for different weights, and let's see how this actually stacks up. Now, stochastic gradient descent. SGD refers to an algorithm which operates on a batch size equal to 1, while mini batch gradient descent is adopted where the batch size greater than equal to 1, right? We refer mini batch gradient descent as SGD, right? It's like a misnomer. For example, you've heard of Xerox machine, right? What is a Xerox machine? Xerox machine are not photocopiers. Xerox machines are machine manufactured by Xerox. But you take a look at an HP machine and say this is HP Xerox machine. See what is happening? We get used to a word so much that we in fact forget what actually this means. That is what is happening with SGD. When you're saying SGD, you're actually saying mini batch gradient descent. You're not saying HGD, because if you say HGD, there's a batch size of 1. So we are not true in the sense when we use the word HGD. Okay. Now let us assume that we have a loss function which looks like this. Xi is the image coming in, yi is the prediction we are interested in, and theta is the weight we are looking at. Now where x is a sample input, exactly what we discussed, a loss is going to be 1 by n. Okay, now you are looking at a batch. Okay, so we have a batch of n images. We are going to look at the loss of every single image, and then we are going to take a mean of that. The part very clear? This should be very clear. So we have our n images, we take a mean of our n images, and that becomes our new loss. This is the loss value which we use to calculate our weights, because I want to update my weight with respect to every single image which I have gone through. I can't update my image once, right? So this is not SGD. SGD would be only one image, so there's no need of this summation here. But because now we are working with a batch, we have converted our SGD into mini batch gradient descent. We will have this summation. I need to take an average here. There's a good thing and bad thing about this, right? Let me share the bad thing with you. Because we're taking the average here, let us say, and this is easy to understand in your context. Let's say you had an exam. In an exam, you had English, you had maths, and you had physics, you had chemistry, right? And you had the social science also, or sports. Why not? Let's say we had sports here, right? So English you scored 75, maths you scored 100, physics you scored 50, chemistry let's say not 50, let's say 80. Chemistry as usual you scored 50, right? Sports you scored 100. So you are a very good mathematician, and you have a very good sports skills also. And let me make it 70 just to keep calculation easy. So let's see what is the total now. Total is going to be 100, 200. Then this plus this is 120. So 320 plus 80, 400. The total is 400. 400 divided by 5. That gives us 80. See the update which you're sending network, that in maths you are 80, and in sports you're also 80, even though these are your best subjects, and you're sending an update in chemistry you're also 80 because we've averaged it. So it's not an ideal way of doing things, but there's no other way actually, because if you go with a lot of images, you can't back off just for one image. You have to somehow capture this data internally, and that is why the training of data is very complex, and your intuition is also telling you that there should be some way in which I can update my weights differently, right? The weight which is linked to English now or chemistry now somehow should get an update that you need to move fast, as compared to mathematics, where we don't want to update any weight now. We are already at 100, but unfortunately because of this guy we can't do that, right? We are going to see this in future session, that how do we handle such a situation, but because of the averaging we are suffering from this, right? When you are looking at your resident accuracies of 86%, I am not sure how many of you are actually going and checking your class accuracies. If you see the class accuracy, some classes are doing very good and some classes are doing bad. So instead of just trying to push your 86 to 89 just by training every single class, where some classes which are already trained, you're just still pushing them, you're actually disturbing them. So idea would be to figure out which classes are actually good and then focus on the classes which are bad. So a very advanced concept, we are going to look at that later on. Okay, now let's go back to our equation. This is the vanilla HGD. Now we are saying, when we are saying HGD, we are again going to fall in a trap where we are saying the Xerox machine. This is the vanilla mini batch gradient descent algorithm, is based on the theta update rule which we just saw. Now this is the update again shown, but in a different manner. So theta t plus 1 equal to theta t minus alpha delta theta, which is the gradient of our loss with respect to theta, right? The same equation written in a different format. Now this is actually what is happening. We start at a specific point and we are able to move this in a particular direction into our point, into the theta optimal point where we want to stop at, right? Now theta optimal is the global learning rate where we want to stop at. In the standard optimization problem with particular requirement, the algorithm converges with a limited number of algorithms. So if the problem is simple, if the curve or the loss function you're looking at is simple, we can easily find a solution. But as I told you, this is not how a loss function looks like. A loss function is going to be very different. Now how should we imagine a loss function? The easiest way I've found, which can immediately give you intuition of how do you understand loss function, is that imagine that your loss function is actually a fighter aircraft. If your loss function is a fighter aircraft, your weight parameter is a heat-seeking missile, right? That is what is happening. Now when this is moving, this is also moving, right? Which means that if this moves, I have to also move. I can't just keep on going in the same direction. So I have to have some way in which I can learn about a direction also, right? Now, in the old cases, in the old, let's say World War One, you have an aircraft, or World War Two, you have an aircraft, you have another aircraft, and we shoot a gun, right? The bullet is going like that, and you know that aircraft just has to take a small turn and it will get saved. Then, and then further advances came in, and then we made what? We made heat-seeking missiles, which means that this aircraft is hot, so when I throw a missile now, it is going to figure out that that's a hot part and it's going to track it, right? But this was, let's say the tracking algorithm was based on the velocity. If the tracking algorithm was based on the velocity, which means I'm going to find the velocity first, not acceleration, which means it would have already moved by the time I know that this is moving, right? So the updates are going to be slow. So in the third generation of missiles technology, we actually started making accelerated missiles, where we can actually track the object, and not just distance or the velocity, but the acceleration also. So by the time it's moving, I already know I should start moving, right? So see how this is going to help us, and we are soon going to integrate this back in the equation. Now this is an aircraft, and aircraft is moving like that, but this is a gun, so it just moves straight. But if we were making let's say a heat-seeking missile which can track the velocity now, right? That means that when my aircraft is moving like that, my missile is going to at least get lag, but still able to follow that. But if I actually track acceleration, what will happen is that by the time the missile starts, the aircraft starts moving, I'll already know that I have to also move and actually target it earlier. So you see, first we have this distance. This is where aircraft is, and this is where missile is. That's a distance. Just throw. Not a good thing, because as I told you, loss curves keep on changing, which means our aircraft will change. Because our aircraft is changing, then we went to the velocities, which means that I can actually look at the velocity. It has some idea about the change in direction, but there's a slower update as compared to if I can directly track the acceleration. Because if I can track the acceleration, I can predict what's going to be in the future to future step. See, in velocity, you're predicting where the aircraft is going to be in the next step. In acceleration, you can predict where your aircraft is going to be next step, right? It's a secondary variable. So if I can track acceleration, I can actually start predicting early on and actually hit like that, right? In velocity, I have to go like that. So I have to calculate more number of steps. You're going to see how we actually link it back. Okay, but this is what is happening right now. And you see, there's so many different directions I have to move before I basically come to my point. Isn't it be ideal that I can directly start from here and end here? Should there be any algorithm which can start from there and just go in this specific direction instead of this shuffling? That is something we are going to solve. But this is easier than done. Even this thing which we are seeing, the curve on the screen, is also is easier said than done, because things don't work in this particular manner. Now, what happens is, first of all, we have these points. These points are called saddle points. Now, in saddle point, what actually is happening is, this is a loss curve. We want to go at a particular minima. But unfortunately, we are stuck at a specific point where if you increase, think of it like this. There's a parameter which is stuck in such a way that if the parameter increases, your prediction for cat increases, but the prediction for dog reduces, right? And let's say the parameter, sorry. What we're trying to say is that, and this happens a lot in the, this used to happen a lot, you're not seeing any of that because we have far more advanced networks now. This is a parameter where if you increase this parameter, your cat is going to be good, but your dog is going to be bad, right? So your cat improves, but dog reduces. But if you reduce the parameter, your dog goes up and your cat goes down. What do you do now? This can happen in the early stage of the network. So we have some ways. In fact, you already are using some of the ways. So you'll never be able to come to this particular problem. So this is called a saddle point problem, where you have equal distributions of weight pushing the loss in a specific direction, but another set of weights trying to push the loss in some other direction. How can you understand what exactly is happening? 90% of the parameters right now are asking a particular, let's say a particular. So if I change the 90% of the parameter, my loss reduces. By changing these 10% parameter increases the loss. Let's say that's the kind of situation we are in, right? Because we are predicting some classes properly. That's the saddle point for us. Now, how 10 can actually affect 90? Because the moment you change this a lot, your loss value increases a lot. So we can get stuck in such a points, but you're not going to see these kind of points directly. What we can see is these points, which are called plateau. Now, what happens in plateau is that you are so close to your final value, and let me show you what do I mean. Let us say that you want to be at 0.324556. In fact, let me use this. Let's say you want to be at 4697.3245678980. Let's say this is where you are, right? And we are working in a learning rate or update in such a way that you have arrived at something like this, right? So you are at 3, 2, but now at 0.000000. So compared to these big numbers, right, you are at a plateau, right? Because let's say this is a hotel bill, and this is, you're just going to just ignore that, which means you're at such a flat plateau that your weight, which is here, from here moving here, is so slow because they are so very close. But unless you reach that particular point, your network is never going to converge. So this is also a big problem. This is called a plateau, right? So we get stuck in these 2 points. And how do we actually come out from these 2 points? Right? That's the question we have. Now, what is the reason? What is the problem here? Problem here is that if I go in this direction, I see an increase. If I go in this direction, I see an increase. I need to go in this particular direction, right? That's the direction I want to be on, or the other direction I want to be at. But this is saddle point, right? This is not very clear how it looks like, but this is the, why is it called saddle? Because the saddle is what you use on a horse, right? So on a horse you have a small thing, right? And then it falls back. Let me try and draw that so you understand how it looks like. Okay. Okay, so this is that down thing, and then apart from here, here you have this curve, right? And apart from there, everywhere you go, you have the higher point, or better would be that. Not an ideal saddle. This. Okay, let's use this anyways. Open image, new tab. Okay. Now, what is a saddle point? See, what happens here is, it's not a very clear, again a very clear distinction, but I can't get a proper curve for you. See, at the center, you have a depression, right? So you have this depression. So if you can follow my hands, okay, you can only follow my hands. You can see my hands. Yeah. So if you can follow my hands, imagine that I have something like this, right? So at the center, there's a depression, and that is where the parameter is. Everywhere you see from this particular point, there's uphill. So here is an uphill, but on the sides it's like that. Those are the curves. So our saddle point looks like this in this axis, but this in this axis, right? So here, of course, I can't move. I can't move because loss is going to increase, and this cut is something like this, which means that if I take an effort to go to this particular point, then I can go down, right? Which means that what we're saying is that if I can take an effort to go out from here, which is increase my loss, then I can go down. That is what we are looking at in this image also. This is what so copy paste in Windows fails for the first time. Let's see, can we paste now? Oh, thank God. Okay, so what is not clear is that there is actually depression here, right? Imagine that there is a depression here, and then we can come up, which means that even you think that it can just slide down here, right? That is what this curve is not has not drawn properly. So this curve is actually like that. So which means that your weight still has to take that uphill battle to go down, and it's confusing. How do you figure out something like that, right? This is not a maxima, this is not a local minima also. We can say sort of local minima, but the local minima generally assume that you have something like this, right? And then you have this on all the sides. But on other two sides, we already know that we have this uphill, right? So this is what a saddle point is. And plateau, is a straight line where the gradient is so small that we are not able to figure out exactly how long it's going to take for us, or how big steps we can take. Now, how do we fix this problem? The solution is actually very simple. The solution is called gradient perturbation. Now, a very simple approach to solve the particular problem, or these two problems, is gradient perturbation. Let's see what exactly we want to do. The problem we have in this plateau right now is that our gradient is 0, right? Very small. So the way we can fix that is by changing a gradient here. Now I've shared this earlier with you that the way we like to change the gradient is not by changing the complete loss curve. So we will like to change our gradient just like that, right? And now when I zoom out, this is a straight line, but wherever my weight was, I have a gradient available there. So I like to just add a bit of noise in the loss in such a way that I get that gradient automatically. I will not like to disturb my loss function at all. Same thing happens in that, let's say we are drawing that saddle in 2D, we are stuck here. We apply a gradient in such a way that actually gets some speed to go out, right? So in both the cases, we see that we add this noise, and that is what we are going to be doing. And we call this gradient perturbation, that we actually shake systems, right? Again, imagine that we have kept something on flat on top of this, but if I shake, it is going to go out, and that is what we're interested in. Now, when we shake, is going to go in the right direction? We don't know, but definitely better than just sitting at a specific point, right? So we are going to shake things, and when we shake things, hopefully it's going to go in a direction we are interested in. So what exactly we do? We take our theta t plus this is the old theta t plus 1 alpha. You are sure what this means. You look at this loss function. We are adding a bit of noise there. So whatever the gradient we are calculating, we just add a noise there, because if the gradient was 0, because we were stuck in plateau, right? We are stuck in plateau or a horse saddle. In both the cases, gradient is 0. When we add this noise, the gradient is not 0 anymore, and this is a noise picked from a random distribution. What is the benefit of picking a noise from random distribution? It's going to be very small, because that is what you're going to be picking from, right? Let's say we pick a Gaussian distribution -1 plus 1, so it's most of the time going to be 0, but sometimes it's going to be a pretty big number also, and that is going to make it jump out of this particular system. That's what we're going to pick. Now this is sigma square, so we have a range. So sigma, depending on what the kind of noise you add, it can jump out, right? So that is what we're interested in. Now the variance should be carefully chosen. For example, it could decay exponentially during the epoch, right? However, this method is very simple and effective solution. So let's look at how we would do this in PyTorch. It's like local minima in all 4 directions. That's correct, Prasad. Now a class add Gaussian noise, we initialize that. We call, what exactly are we doing here? We are taking a tensor, we are adding a bit of random noise here, right? And standard deviation and mean. So this we have to pick and add, and we basically send that back, and in the transforms we call our add Gaussian noise. That's all. Now good practice is what? This comma. Always make sure that you end your transformations or anywhere where comma is required by additional comma, maybe with tuple or something else. So very, very good exercise. Okay. Now I would say that we are indirectly doing this. Why don't we have to do something like this? Right? What I'm telling you is that this is a very good thing, adding Gaussian noise, but we are not doing it. And now I'm telling you that you are already doing it. So there are 2 ways in which we are already doing it, and the way A and B are in the quiz. So you have to answer this question in the quiz, that how do you think we are already doing this? How do you think we are already adding noise to our loss function? Just think about that, okay? It may not be very evident, and definitely L1, L2 is not the answer, okay? Now let's look at momentum and Nesterov. It is never a good idea to interfere with the network, and in the previous approach we were doing exactly that. Okay, what exactly were we doing? We were saying that we are going to calculate a gradient and directly we are going to add a gradient, and we discussed earlier also that we like the system to figure out that what exactly should be done, right? So we want to do something like that. A more robust solution is provided by introducing exponentially moving averages, right? The idea is very intuitive. Instead of considering only the current gradient, we can attach part the history to the correction factor, so to avoid abrupt changes in the surfaces become flat. Okay, so this right now we're talking about momentum. Let's see the equation, right? And let's see exactly what's happening. Earlier, when we had a fixed learning rate, what you said that calculate that delta L by delta theta. Now let's look at exactly what is happening. We were saying calculate delta L by delta theta, which is going to be the rate of change of that aircraft with respect to time, right? So you've done a rate of change of aircraft with respect to time. Because of that, now you are able to track it. Perfectly fine, right? That is what SGD is. It is able to track our systems properly. But now, if you see this equation, indirectly we are actually doing acceleration. Let's see how. It's so frustrating. All right. Now, this is the SGD with Nesterov momentum. Okay, now let's see the equation. Our theta t plus this guy is equals to theta t plus 1. Okay, now let's see what is this guy. This guy is equals to this guy. First of all, when time is equals to 0, this is equals to 0 because there is no before time. So when t equal to 0, this guy is equal to 0, vt minus alpha into this guy, which means at t equal to 0, this is not there, and this is equal to this guy, which means I can just remove these guys, and that becomes my equation, which is the original equation which we saw, right? That's the equation of SGD. But when t is equal to 1, when t is equal to 1, yeah, when t is equal to 1, this vt plus 1, right, is equal to mu into vt. We are going to see what is mu into vt. And what is vt? Vt was last update we had, so vt is going to be, right, gradient, the last update we had, the gradient of the L theta, so the last update we had. So what is actually happening is, this is a vt and this is a vt plus 1, so we are updating a theta t plus 1 considering the last theta also, which means that, and we have this mu also. Okay, so let's see the equation. What is the equation saying? Equation is saying is that this is our normal update, which we use anyway, so that is not a problem. But if you basically add both the equation, because I want to show you what exactly is happening. If you basically add both the equations, our equation becomes theta t plus 1 equals to theta t plus, right, this is theta t, mu into vt minus alpha, right? That is the equation which we have now. So you realize this is actually the old thing only. There's not much difference here, right? But this guy is the last update we had. So what we are saying is that I'm going to take 90% of the last update and then the current one. That is exactly what we're trying to do here. How this helps is, if we were moving in a straight line in the last step, right? Let's say, let's look at it from a downhill direction kind of. So when we were here, our last update was to move down fast, in a speedy manner, because that is the gradient we had. But the new update, which is about to come, is going to say to slow down, right? So because the new update is on a flatter plateau, it's going to say slow down. But the last update was to move faster. Remember, these are vectors, guys, right? So this plus this vector, if you not do that, because of the last update, I will actually still move faster in that direction. So this is momentum. The mu term is the momentum factor, which you are adding as 0.9 in SCD or some other value. So this, what have we done here? I've taken the momentum, right? And momentum is what? If you look at physics, momentum is going to be speed into your weight, right? Which means mass into velocity. So I've taken velocity and I'm using the current velocity. So I have two velocities, right? Whenever we have two velocities and we are adding them, we actually have sort of acceleration, right? Because this is the last time, this is a new time. So I have this delta t factor also inbuilt. So this is what we have done here. We have taken a kind of acceleration here, not directly but indirectly in this specific case. This is called the momentum algorithm. So what exactly is happening in momentum is that, let's say I'm following a particular curve. Based on the last update we have, we're going to take that update and we're going to add it to the new update. But I have to make sure that how much preference I'm going to give to my previous update versus how much preference I'm going to give to my current update. So we take this as a value between 0.75 to 0.91. Okay, so mu is going to be between 0.75 and 0.91. The second term, okay, so this is what is happening in our momentum. Now, Nesterov update, we have equation for Nesterov update also. Now, Nesterov update, sometimes you're going to see Nesterov equal to true or not. In Nesterov, what do we do? Let's see. It's a very interesting equation. I'm going to keep it next to this equation. I need a bigger screen. Okay, let's see. This is Nesterov, and this is normal momentum. This is Nesterov with momentum. Theta t plus 1, theta t plus 1, theta t, theta t, theta t plus vt plus 1, vt plus 1, perfectly fine. What are these? These are the momentum terms which we are adding. Vt plus 1, vt plus 1, perfectly fine. Mu vt, perfectly fine. Let's see that. This is alpha alpha, theta theta, L L, theta theta. Okay, but we have something else here. We have theta t plus 1. Okay, so what exactly are we doing? Let's see where this is coming from. This is coming from this guy. And what is this guy? This guy is equals to theta plus mu into Vt. Okay, you see what we have done? We've taken the last update we had. We take that update, first update our theta, then we get this new theta. We take this theta to calculate the gradient, right? And then use this new gradient to update our Vt plus 1, and then we enter Vt. So we have done two steps here. So what exactly we were doing till now? We were saying that this is my theta, and this is where this is the momentum term we have, right? And we just add a momentum term to this, multiply this v. This is what we were doing. Now what we are doing next off is, this is where I am, this is the momentum term we have, multiply with u. So first we take this, update an intermediate theta, we call that, let's say, theta dash. Look at where the theta dash is, right? So indirectly we have sent it to this particular location. Indirectly, we have not gone there yet. At that direction we calculate the gradient again, right? That is what this part is. We calculate the gradient again at that point, and there we realize, oh, we need to be here. So we directly jump like that, and that is what this equation, this graph is trying to tell you, right? If you see both the graphs, this is the momentum update and this is the desktop update. In momentum update, we take the last, we take the new, and then we go in the center axis. That's the update we have. In desktop, we do, what do we do? This was the momentum step. We go at that step, we calculate where we want to be, and then from here we directly go there, right? So there's slight differences, and generally people use desktop and momentum either way. Momentum on without desktop, both are nearly same. There's no consensus of what should be used. People have preferences, so you can use desktop also. Okay, so that's the nest of momentum for us, right? So what is happening is that in HGD without momentum, right, when you don't have momentum, you will just keep on shuffling. But when you have momentum, see, last time I went like that, this time you're asking me to go like this, right? What exactly I'm going to do now? The vector is going to be straighter. So basically we are fixing what problem using momentum. Let's see that. Last time you sent me like that because of the loss function. Now you're asking me to go like this, right? I actually want to go like that. So if I have the last update and if I take the new update, what is the axis going to be? The axis is going to be this for the motion. That is exactly what we're solving. So we don't suffer like that. We don't move like that. We move like this towards a point. I'm not drawing a loss curve here. Please remember, I'm drawing the motion of the changes in the directions of W. We don't want to shuffle a lot in two axes. We directly want to move in one specific axis. That is what we're interested in. Okay. So till now what we have covered is where we have one alpha, and that alpha is fixed for every single parameter. I have 10 billion parameters and my alpha is fixed for every single parameter. That is what we've discussed till now. Okay, now let's look at where alpha is different for every single parameter. Okay, now the first algorithm in that is called RMS prop. This algorithm was proposed by Jeffrey Hinton. He is like Superman in machine learning. So if you are a student, you are going to use RMS prop for everything. It is based on the idea to adopt the correction factor for each parameter, right? That is what, who was that? Shashank was also asking, I believe. Yeah, Shashank was also asking. So Shashank, you are as good as Jeffrey Hinton. Okay. It's based on the idea that to adopt the correction factor for each parameter to increase the effect on how slowly changing parameter and reduce it when their change magnitude is very large. This approach can dramatically improve the performance of a deep network. It is a little bit more expensive than momentum because we need to compute the speed term for each parameter. Now, of course, this is written by someone who is in favor of the algorithm, right? Because it says that it adds slightly more expensive than momentum, right? So you have 10 million parameters and you have 10 million motion updates for all of them, and you have 10 million momentum updates and parameter, and you realize how many parameters and stuff is there. So there's a huge overhead when you use ADAM or SGD for big algorithm. If you're using for MNIST or if you're using for small networks, you're not going to see a lot of difference, right? But it may actually be very expensive for big and deeper networks. Does momentum reach faster to higher accuracy? Yes, momentum reaches higher to faster accuracy. Now, let's see this equation. We have Vt plus 1 into theta t, and then we have Vt, okay, not into, this is the function call, okay. So we have Vt plus 1, right, the t plus 1, mu Vt plus 1 minus mu into the last theta. What is this? This is called Sloyak equation. What exactly are we trying to do here is we are focusing more on the update right now and less on the other guys, right? So this is called a moving weighting average, moving averages. This term computes exponentially moving average of the gradient squared. Just like momentum, we will determine how fast the previous speeds are forgotten. The parameter will do. Okay, we're going to look at that. Basically, till now we had just mu here and we had nothing here. But now we have mu here and 1 minus mu here. So this mu becomes a balancing factor. It says that take the new update more, take the less update more, and based on that, we can actually update our focus on. Should we focus more on the past update or should we focus on the current update? So that is something we have to figure out. Now our update terms for each theta now becomes alpha minus theta minus alpha divided by this term. And what is this term? This term is coming from here, right? See what we are doing here, we are actually trying to calculate how alpha should be, right? This is allowing us to calculate how alpha should be for a particular parameter, and this is something we have to calculate for every single parameter. Now alpha is the learning rate, theta is a small constant. This is required. Why is this required? This is required so we don't do a divide by 0. As it is possible to see, each parameter is updated with a rule that is very similar to vanilla stochastic gradient, but the actual learning rate is adjusted per single parameter using the reciprocal square root of the relative speeds, right? So what is happening here is, look at what is happening here. My last update was small, the new update is also small. Based on that, I'll be able to figure out this particular guy, and that is going to help me understand that my updates needs to be even smaller, because that is what is helping me. So you need to spend more time on this. I'm not going to spend time on this guy because I'm soon going to arrive at a specific point for you. Then we have Adam. Now in case of Adam, see what we have done. We have VT, right? And this VT is the same as this VT, where we are trying to calculate this new momentum term for every single parameter. But now look what happened. Here we had the loss term. Here in Adam, what we have done, we have taken this loss term and just one second. Yeah. Okay. First of all, our theta here is theta t minus the thing at the bottom. The thing at the bottom is the same as the last one, but on top we have this dt term now. Just dt term, if we see on the back side, was loss for us, but now this is what gt for us. Now what is gt? gt is this guy. So as we have seen in case of ReLU and SReLU and PReLU, that when things are simple, we like to tend to make it complicated. We think we have an intuition, and based on that we do that. So what we have done here, we are telling ourselves that okay, our weight has a momentum, but our loss also has a momentum. I told you that our loss curves keep on changing. So what if the loss was changing faster automatically in this direction? So we take that amplitude also and we add it back. That is what we do in Adam, right? So what do we do in Adam? First of all, what is HGD versus other guys? HGD is a fixed learning rate algorithm where the learning rate is fixed for every parameter. Second approach, the learning rate is different for every single parameter. How do we calculate that difference? We calculate that difference by using this speed. We look at the last momentum of that weight, we look at the new momentum of that weight, and that allows me to figure out that the current momentum should also be faster or smaller, and we have a specific equation for that. Then we move to Adam, where we say that not only our weight is moving, the rate at which that weight is moving towards the loss is changing, our local minima is changing, my loss curve itself is also changing. Because my loss curve itself is also changing, I can figure out whether loss is increasing or reducing based on how other millions of parameters are changing. So based on that, I update my equation for the weight update. So now we have GT term and VT term, right? So that is what we have. Now, which one to use? Okay, now this is the graph which shows, let us start again. You see, so HGD is a red guy, right? Look at the red guy, like poor. You've seen Tare Zameen Pe? Doesn't this feel like Tare Zameen Pe? All the other kids are like fast and approaching the assignment and finishing the class, but HGD guys, like poor guys, not even moving, right? And now look at this graph. This is the saddle point. Again, everyone, even HGD, even momentum has also gone through, but HGD is still sitting there, right? Now let's look at one. I want to explain this through an image to you.
Guess what I just got? Hello again.
Hi.
That's a big phone.
With all of your conniving, you lost your charm. You built a flame and warmed my heart, but your lying and cheating has torn us
You gotta send me that
apart. And I'm moving on. I'm gonna find somebody out there that will surrender to me in the loving care. Oh, I'm moving on.
So I've just picked a random ad from Samsung, and you can pick other ads from other guys also. What I want to tell you is that if you look at that ad, doesn't it feel that iPhone is such a bad phone, right? No headphone jack, no wireless charging. The new ones have, of course. Like we can decipher the ad more. So when Samsung is going to make an ad, it is definitely going to make sure that Apple looks bad, and that is what is happening here. Marketing ad. Please don't get fooled by this. Okay, look at the real curve. These are the real test results of the of running the algorithm. We have this HDD in black, and then we have this hybrid, which is HDD with momentum, and then we have add a grad, we have RMS prop, we have Adam, we have Adam default, and you see that CIFAR 10, CIFAR 10 test, in both the cases, there's no one which is going to come close to HDD, right? What actually is happening? See, our loss is dependent on millions of parameters, right? If you are trying to figure out that, first of all, look at what we're saying. We are saying that we have a partial derivative where we are assuming that every one of them is constant, and then we're calculating this, right? Now we are saying no, but maybe my changing one single weight has some dependency on the other one. Other one should be changed more as compared to this one. So you go and change the other one more. Now you have just broken that differentiation or the partial derivative rule. What you've done is that in the partial derivative rule, we have changed it slightly, right? When we were using partial derivative, we were saying everyone is going to be changed very in an equally small way. But now because you have this new term, which is not changing these terms in a slightly different way, your partial derivatives are not accurate, right? This is my intuition, by the way. There's no paper which claims that why SGD is better than the other guys, or why other guys are not as good as this, right? So I'm going to still share with you where exactly we do this. This is a validation curve. Again, if you go to any other online source and you try and figure out which one to use, you're going to get curves like this. Let's see what is happening here. HDD is red. Okay, bad here. HDD plus momentum plus Nestor again at top. Right? There's no way you can beat HDD. This is HDD and Adam. Again, we see Adam here. We have HDD here, right? But okay, this curve is not shown properly. Okay, we have the HDD with momentum and the other guys, right? Now, this is the training accuracy, by the way, right? This TRN accuracy. What is this? This is the validation accuracy. So you are always going to see that your test accuracy is always going to be more in case of HDD as compared to your training accuracy. Training accuracy might be low, and this is what we will focus on. But we don't want training accuracy to be high. We want the validation accuracy to be high, and there's no one who has beaten the validation accuracy. Still not convinced? Let's look at this. Adams and others are generally have lower training error loss, but not validation errors. It is common to use HDD for SOTA performances. SOTA is state of art. Now, if Adam, HDD, AdaGrad, AdaBoost, AdaDelta, or EVA4 or other algorithms were so good, why are we not seeing any state of art results on that? ResNet, DenseNet, ResNext, right? SENet, NASNet, ENAS, in fact, VGG, in fact, your Inception V1, Inception V2 was Adam. Exception, all the algorithms we have heard of is trained on HDD with momentum, always. Now this second thing which I also feel is happening. Now HDD is fast as compared to Adam and other guys, right? Why is it fast? Because there's no overhead of calculating your parameters or the alpha for every single variable. And these networks are heavy. We have 100 million parameters, which means we have 100 million momentums, which means you have 100 million loss values also. So you see the overall number of computation which is required is very heavy. So again, if you think from the ResNet approach, that instead of actually going for this 200 million of overhead, I can actually get a better network, bigger network, and train with HDD with that. So maybe that is what is happening. But what we're seeing is that for object detection and object recognition networks, we are using HDD. There are some caveats, and there are asked in the quiz also. However, when your data samples are low in number, when you have very few images, you are going to go ahead with Adam or others. You are not going to go ahead with HDD. HDD is not used for when the data sample is less in number. HDD is not used when you are doing transfer learning. In transfer learning also we are seeing Adam and other guys. HDD is not used when you are using reinforcement learning. SGD is not used when you're using NLP or LSTM or RNN. SGD is only used for object detection and object recognition networks, which we are working on right now. So the moment we go for reinforcement learning phase 2, or we go for object detection at the end of this course, phase 1, we are going to be using SGD now, but the moment we hit reinforcement learning, we're going to go for Adam and other guys. Does momentum reach faster to higher accuracy? Yes, I guess. Yeah, the precise answer is yes for this. Momentum reach faster to higher accuracy? Yes. Okay, Adam and others are preferred for GAN as well and Q learning. SGD needs much lesser memory since it only needs first momentum. It has much better regularization property compared to Adam. If you are interested, you can read this. And if your data is sparse, which is going to be likely when you are going to work on your own custom data set, we are going to use for adaptive learning rate metrics, right? This is a empirical evidence. There is no paper which confirms that. This is what we are seeing empirically, right? These are very complicated systems where people have not commented on yet. Now, this is a completely different approach. So right now we are approaching that we need to change our learning rate. Okay, today what we have covered, we have just understood how the weight decay, how the weight update happens, what SGD is and what other guys is. We have not covered how do we actually change learning rate. So we are still not going to answer that. But see what is happening here. There are two approaches. Schedules for a learning rate, that we figure out a particular point after we reduce our learning rate. That is one approach. Another approach is we change the batch size. It's a very weird approach. What we are saying here is that let's say, and this number is again we have to find. Let's say for 50 epochs we have batch size 32. After 50 epochs we change the batch size 64. Then 128, then 256, and so on. This is also effective. Now, it should be very clear that the left is what academia is pursuing and the right is being pursued by people like Google and Nvidia. Of course, they would like you to use why would the batch size changing affect us? Okay. Can you think now? Okay. Simple answer, a simple question. Where do we use batch size in loss function? The loss gets divided by the batch size, which means if we double the batch size, the loss is going to become average loss, not a full loss. Right? Average loss is going to become smaller, which means your gradient updates are going to become smaller. So that's the intuition. So either you change the learning rate, or you double a batch size or change a batch size. When you change the batch size, again your learning rate, your loss is going to become smaller, which means updates are going to become smaller. So that's the background behind that. But we're not going to do that. Now, learning rate, we discussed this also, that if it is very high, we are just going to shuffle out. We are not going to basically come to a minima. If it is too small, we are going to take infinite time to reach our local minimum. We have to find out a particular learning rate. Now, that is what you're going to do. Now, again, this image is taken from Andrew NG. If you're interested, I request you to look at this video. It's a very good video. We basically want to move slowly. We don't want to move fast because we might actually jump out, but there can be an optimal way of jumping also. So we need to figure out what is an optimal way. The training, okay, now look at this. The training should start from a relatively large learning rate in the beginning, as random weights are far from optimal, and then the learning rate can decrease during the training or allow for more fine-grained updates. This is one point of view. What is this point of view? Let's start large because we are far off and then slow it down, right? This is one point of view. Please remember that, because in the next session we are going to say something else. What is this line saying? This line is saying that we should do something like this, where we start at a large learning rate and then we drop, right? And the reason we are saying we are doing this is because we are already far off from where learning rates manually and trying to figure out what is the right value, but not a great approach. Leslie Smith, he's a very great gentleman, a great guy, old but very knowledgeable. He introduced something called cyclic learning rate. This is what we're going to see in the next session. Here you can find learning rate. So we are going to use the first part of his algorithm, which is to find the learning rate. And in the next session, we're going to look at the cyclic learning rates. The trick is to train a network starting from a low learning rate and increase the learning rate exponentially after each patch. See that? This is a different approach, but this is for something else, okay? So let's see, let me not confuse you. This approach is for the full training of the network, okay? This is for the full training. This approach, where we are saying the trick is to train a network starting from a low exponential rate and increase the learning rate, is for finding the learning rate, right? Here we are trying to find the learning rate. What we're doing now is, we are going to take a network and we are going to slowly increase the learning rate, right? Increase the learning rate from a very small value. So you can see we start from 0 and then we end at 400 epoch, and we are changing the learning rate from 0 to 1.4. So we change our learning rate in a range, and we are going for iterations here. These are not epochs, right? It is senseless to train on network 400 epochs to find out the best learning rate. That is useless, senseless. So what we are doing is 400 iterations, which means 400 batches only. Maybe just one epoch. So what we're doing here is, we're going to start with a small learning rate and we're slowly going to increase the learning rate, and we are, this is the loss curve you're seeing. Basically, this is the learning rate change you're seeing. What is going to happen is we're going to plot our loss now, just for this one short epoch. So we have different kernel to extract different features. We can different each kernel rather than each parameter. Not proven to be ideal way. Network would automatically figure out similar values for anyways. Okay, so what is the algorithm? This algorithm is different. We are not training the network from scratch end to end. We are trying to figure out the best learning rate. So what do? We take our network, or the network you are going to be training. We start learning it at zero and we slowly increase it, right? How many iterations have happened? We have seen 400 iterations happen. In these 400 iterations, we are going to plot a loss curve. Now, that's the point. Where you see the your loss becoming small, that means that the loss was reducing very heavily at that point. That's the starting learning rate which we are going to pick, right? That is how we get to learn our learning rate. The one single learning rate where we should start. But this point should be very clear. Okay. Now, before I end, I want to share something so you don't get confused. This is the most important part of today's session, which is going to link to tomorrow's session or the next session. I'm sorry. So we saw one comment being made that you start at a large learning rate and then you end, right? That is one approach, right? Okay. Now that is the default approach which you are going to pick for this assignment. And we saw that this is what we were discussing, that we want to run this for some epochs, then drop it, then run it for some epochs, then drop it, then run it for some epochs and drop it. I told you when we are doing this, we are saying that apani bhagwan hai, that we know everything, because we are picking this automatically. We don't want that. We want to figure out that our network, our loss, it looks like something like this now, right? Which means that we are hitting some sort of plateau here, that I'm not able to move out from there. So I need to write a method for finding something like this. If you have time, please do that, because that is not the part of the assignment. In the assignment, I'm not asking you to do that part. We're going to do something else, right? So this is one step. So this is called reduce LR and plateau, where you are reducing on its own. It's built in Keras, or you can use some external libraries for this also. PyTorch, it's not inbuilt. PyTorch will have to find something. Yeah, I know for sure that's not inbuilt, but there's still PyTorch reduce plateau. PyTorch. Oh, it's there. Perfect. Perfect. So this is a part of the assignment then. Okay, I was worried that this is not inbuilt. Okay, let me continue here. Okay, a comment on the code is right now. Even though you are going to be using all of this, you cannot directly use this in your main EVA file. You have to add it to your module, and you have to add a method in which you can allow your code to use such a thing in your own code, right? What exactly I'm trying to tell you is that implement use on plateau. Right, so it's already inbuilt, perfectly fine. You have to mention some things, that how much you want to reduce and how many steps you want to do before you reduce it. So let's go back to the point I was making. Okay, so now we have this inbuilt in PyTorch, and you're going to use it. So now our network knows automatically when you should reduce, and generally we reduce it by 10. And what is the reason behind 10? That let's say we are fixing this digit and this digit, now I want to start fixing the other digit. So it's like 10 units away, right? From the earlier digit which we are fixing. That's the idea behind 10. That's the first thing. So what is the first thing? Again, repeating that we start at last learning rate and then we drop. And we don't drop like that, we drop like this in the current assignment. Okay. Okay. Now there's another approach, and the other approach says that this point, which we figure out from that find LR, the Leslie Smith part I told you, right? How do you find LR? This is 300, 400 iteration. Now let's say one epoch, and we slowly change our LR learning rate from 0 to a big value, let's say 1.4, 1.5, and this is how we are changing our learning rate. Now, based on this change, we are going to find that our loss actually does something like this. And wherever we see this dip is going to be the learning rate which we are going to be using at the highest point, right? And from there we reduce, right? That is what we have discussed till now, stitching both the things together. But in next session, we are going to see that we don't want to start at this point. We also want to start at a small point and then hit that point. Right? And why do we do this? This is something called warm-up. If you're interested, you can look at warm-up, but I'm going to only cover this in the next session. So what is happening is we find the best LR that we want to train. We start at a small value. From here we go to this value, and from here we slowly do this. And again, these are not straight lines. These are going to be lines like this and this. Where on this particular side we are using our reduce LR on plateau, and this can be a straight line. If you have to write an equation, and we have to find out exactly when we do this, right? There are many steps involved if you want to do something like this. What are the steps? Let's see. First, we have to find out. So this is called one cycle policy. We are going to cover in the next session. We have to find out this point. What is the highest learning rate to which we can go? Slightly different from what we discussed today. Then, how many epochs I should take to reach that particular point? Then, how many epochs should I wait to reach this specific point? And by the way, this is not zero. This is going to now do something like that, right? So I need to figure out that after these steps, how many steps further I should do. So I have to find out total number of epochs. So this is total epochs. I have to figure out this point where this is the initial set of epochs in which I need to reach my highest point, and the curve, like how many steps should I take before I reach this point and then this point. There are too many things to find out here. That is why this is not your assignment. What is your assignment? Your assignment is to take your model, train for one epoch. In that one epoch, change the LR rate of your model in this approach, this exponentially changing approach, and then draw your draw your loss curve also, and your loss curve might look like that. And wherever you have this lowest point is going to be the point you're going to be using for your LR, right? And that's the learning rate. And you're also going to use reduce LR on plateau. Yeah, you're also going to use your reduce LR on plateau. Okay, so what is the assignment? Pick your last code, make sure to add cutout to your code. Cutout now should be a default. In this assignment, using dropout is not going to be penalized, but in the next assignment, if you're using dropout, it will be penalized. I'm expecting you to not use dropout and replace it by default cutout, right? We don't use cutout and dropout together. So use this repo. Now in this repo, you already have LR finder code given. Move the LR finder code to your module, implement the LR finder for SGD, not Adam. This is implemented for Adam. You just have to change Optim to SGD. Implement reduce LR on plateau, which is here, and find the best LR to train your model. You are going to use the LR finder for that. Use SGD with momentum. You are going to use SGD with momentum, but you're also going to use reduce LR on plateau. So it's going to, so this is basically going to go in the reduce LR on plateau, these values. Train for 50 epochs, show the training and test curves. Target 88% accuracy, run GradCam on 25 misclassified images. See, now assignments are going to get complicated, and if you have done your assignments in the model way, this is literally half an hour exercise, except for the training time you're going to pick. But if you've not done your assignment in a model way, if you don't have the curve, the code for 25 misclassified images now, you're going to take a lot of time. And that is why I'm recommending you to convert your code into modular, so these things are readily available. You can just with one function call them, and run GradCam on any 25 misclassified images, right? So first you have to find misclassified images, then you have to run GradCam on top. You want to see exactly why a model is failing. In the line 9 itself, you will figure out that you predicted dog or that image bad because you were not focusing on some part. We want to learn this particular thing. Why? Because when your accuracy is slow, you can't just keep on changing different learning rates and augmentation without even thinking about that. This is going to tell you that your images are dark, which means you need to add some brightness to your image or reduce the brightness of your images. You're not able to capture faces from the side angles because you don't have enough samples for that. So you probably would like to create more samples for that, and that is exactly what this line is going to do. If you can do this line properly, then you can debug your code, debug your models whenever you want. Then submit. I've pasted the answer, the questions here and the points as well. Paste your S10 assignment GitHub link, 500 points for that. Paste the link or upload the training and test curves. There should only one graph. One graph which shows the training and test curve both. 100 points for that. What is the training accuracy of your model? You're targeting 88% plus. Share the link or upload the image of 25 misclassified images with cracked cam results on top of them. This is 250 points, right? This is very, very important. Please realize that. Further readings, these are some of the points, some of the other URLs I'd like you to go through that. Okay, now further reading. To reduce overfitting, add more data, use data augmentation, right? I like you to search on this and see what you learn through that. All right, so that ends our session today. If you have questions, please raise them. I'm going to wait for your question and then proceed for the end of the session. Basically, the session has ended. If you have questions, you can please ask. As we have different kernels, okay, not proven, okay. Okay, viewers are dropping, which means people don't have questions. LR Finder is for one epoch. LR Finder is for one epoch, yes. We don't call epoch, but iterations. Basically running many batches. Save 405. Oh, I forgot to record that session. Let's see if I can download this.